Hello and welcome everybody to another Kickstarter Colloquium. So as usual, I will just kick off with a quick range of reminders. We are recording this colloquium for the benefit of people who watch them on YouTube later. So if you please prefer not to be recorded, please keep your camera off. And please don't forget that if you're not the one actually speaking, please mute your microphone so that we don't get crosstalk. You'll see that the Zoom chat is enabled, and you're welcome to post questions at any time to either speaker. We'll make sure that there is time after each talk and at the end for some questions and discussion. So, on to today's speakers. I'm delighted to welcome representatives of two of the LSST science collaborations, one from TVS and one from Solar System. First of all, Kat Volk will discuss the dynamics of small bodies in our solar system, followed by Victoria Braga, who will present his works on the survey strategy metrics specific to pulsating stars. So we'll begin with Kat, if that's all right. So I will stop my sharing and you can take it away.
All right, it's going. All right, I assume that is showing up.
Yes, it is.
All right, great. So I'm going to talk about a project on getting us ready to do dynamical orbital dynamics characterization of small solar system bodies as we enter the LSST era. So because this is a mixed science collaboration presentation, I thought I would just start with the big picture overview. Someone's mic is not muted, but the big picture overview of the small body populations in the solar system. So from the sun out here, we have, of course, the near Earth asteroids in the inner solar system, the main belt asteroids between Mars and Jupiter, the centaurs, which are objects on transient orbits in the giant planet region, the Kuiper belt or transneptunian populations beyond Neptune, and then farthest from the sun, the Oort cloud on loosely bound orbits, an appreciable fraction of the way to our nearest stellar neighbor. So the Oort cloud feeds the long period comets that we see in the inner solar system, and the transneptunian population feeds the centaurs and the short period comets in the closer in parts of the solar system. LSST is expected to observe many, many times the number of known objects in some of these populations, which I'll get to in a bit. So we really have to kind of up our game in terms of being able to interpret the dynamics of the things we see. A little bit later, I'm going to focus on just the outer solar system, since this is a short talk. So this is a top-down view of the four giant planets: Jupiter, Saturn, Uranus, and Neptune are the rings here. And then all of the white dots are the known transneptunian objects as of a couple of years ago when I made this plot, but it has not changed appreciably. So you can see a concentration out beyond Neptune's orbit. Some of that is the classical Kuiper belt, which we'll get to. And here is kind of a side-on view, so you can see that they're not all concentrated just in the planetary plane, but there's kind of some vertical structure to this disk as well. Now, there's a lot of observational biases in these. We detect these in reflected sunlight, so we are very biased toward things that come closer to the sun, and we see them on their closest approach as opposed to farther out in their orbits. If we take a look at the orbital distribution of the observed transneptunian objects, here we have plots in perihelion, so closest approach to the sun, versus semi-major axis, average distance from the sun, and then orbital inclinations, of how much their orbits are tilted relative to the average plane of the planets in the solar system, again, versus semi-major axis. 30 is AU is where Neptune is. We got to 90 in the linear scale, and then here's a zoomed out view because we have observed things with average distances out to 1,000 or 2,000 AU that just don't show up in the linear scale very well. And there's kind of four broad categories of TNOs. There's the so-called classical TNOs. Those are things between roughly 40 and 50 AU from the sun on relatively circular orbits. So they're close to this one-to-one line where they're on a perfectly circular orbit in the perihelion versus semi. Then we have these dark blue vertical structures. Those are mean motion resonances with Neptune. So things, for example, in this 3:2 mean motion resonance, which is famous because Pluto is a member of this resonance, they complete 2 orbits around the sun for every 3 orbits that Neptune completes. And this is a special dynamical state that has important implications. We have these red dots, which are the actively scattering objects. Those are things that every time they come into perihelion, they get pretty close to the planets, they get a gravitational kick, and they wander around in orbital energy, which is to say wandering around in semi-major axis. And then the tan are the detached populations. So these are things that are relatively dynamically separated from the planets. They just kind of stay stable on their current orbits. They don't get close enough to get strong perturbations. So this is all recording the history of the outer solar system. In the early solar system, we had the giant planets forming closer to the sun than they are today, within about 15 to 20 AU from the sun. They interact with a planetesimal disk and spread out into their current orbital configuration. And that planetesimal disk, we know that there was a pretty massive disk out to about 30 AU, and that's what gravitationally interacts with the planets to redistribute them through planet migration. This population forms all of the high inclination, highly elongated, high eccentricity orbit, hot TNO populations, after they are dispersed as Neptune kind of plows through them and implants them into the current populations. And then some of those dynamically cold, so low eccentricity, low inclination TNOs are part of the cold classical disk that is a remnant of a lower surface density disk that existed where we see them today. We don't quite know the extent of that, but at least it's kind of in the 40 to 45 AU region in the current population. And models for how the giant planets interacted with this massive planetesimal disk and how they rearranged themselves, including things like there might have been another ice giant that we ejected. All of that leaves signatures in the final populations of the TNOs that we see today. So it's really important that when we observe objects, we be able to know what dynamical class they belong to, because that affects what we can interpret about what they mean for the history of the solar system. And so here I'm just showing the statistics of TNO observations over time. Of course, we had Pluto, Chiron. The black lines here are the cumulative number of known TNOs with kind of well-determined orbits. And we're at, kind of between 2,000 and 3,000 today. This is the number of discoveries per year in the red histogram. And when LSST has been operating for a couple of years, we should have 10 to 40,000 known TNOs. So we're going up, at least an order of magnitude, maybe times a couple. So that's a lot more objects, and we're not really prepared to deal with that from a dynamics perspective. Usually we are dynamically classifying these things kind of by eye. We have some algorithms, but we end up checking a lot of it by eye, looking at orbital integrations to look at the behavior. So we can't do that with 10,000 objects. And there's other things we want to know. We want to know what are called proper orbital elements. We want to know these resonant identifications, stability timescale. Much better job than we currently do typically of accounting for the uncertainties in the observed orbits. So, for example, proper orbital elements kind of filter out some of the perturbations that are happening due to the current solar system. So orbits are perturbed by the planets. This is showing the giant planets themselves and how they perturb each other over time. Their orbits kind of precess and wobble and elongate and circularize just by perturbing each other. And you can imagine that if you want to get some information about kind of the quote unquote original orbit, you'd want to remove some of those perturbations, so filter them out. And the same thing applies to small bodies. Their orbits circulate, precess, all these sorts of things due to the perturbations of the present planets. And when you just take the snapshot of their observed or osculating orbital elements, which is what we get directly from the observations, this is an example of what a part of the main asteroid belt looks like. And there doesn't appear to be much structure there other than you can see a mean motion resonance. But when you filter out these perturbations and calculate these proper orbital elements, you see a lot more structures. That's the bottom plot here. You can see some mean motion resonances pop out more clearly. You can see this one has some things in the center of the resonance, whereas this one has kind of evacuated things from the resonances. You see horizontal structures, which are collisional families. So when asteroids collide, they spew fragments, and those fragments will all share the same proper orbital eccentricities and proper inclinations. But if you just look at the osculating, you don't see any of that structure. Things we want to be able to calculate for all of the LSST observed millions of asteroids. We also want to know about resonance occupation. As I mentioned, there's a lot of mean motion resonances in the TNO populations. And for example, it's really critical for deciding what do these so-called detached or extreme TNOs mean for the history of the solar system. If these things are actually in Neptune's resonances and we only think they're detached because of bad orbit fit uncertainties, that means something. If they're dropouts from the resonance, Neptune is migrating, that means something else. If they are completely unrelated to Neptune's resonances and they have some interesting structures, maybe that's telling us about a distant unseen planet or possibly a rogue planet in the early solar system. Or they could even record perturbations from like passing stars in the solar system's past, or kind of the effects of the birth cluster when the sun was in a much denser stellar environment. But all of this relies on understanding their current dynamical state so that we know what the current planets are doing to them. So it's really important that we understand how the resonances are sculpting them. Another thing that's important to understand is the current state stable for gig years? So what we see is what we had at the beginning of the solar system, or is it transient? So something that's just temporary. For example, the giant planets, I think they all now have identified Trojan or co-orbital bodies with them. Some of those co-orbital populations are gig year stable. They were captured in the era of planet migration. And others are just transient, kind of flying through, temporarily co-orbiting with the planet and leaving, like this first Uranian Trojan that was identified. So these are important things to understand about the orbits. Doing the orbital integrations of observed objects has been made very user-friendly by the Rebound Orbit Integration Package. It has really revolutionized and opened up the ability for people to run dynamical simulations. But we haven't actually made very many strides in analyzing those integrations because you have to know what to do with the outputs of those things. So that is what we're working on, is a nice user-friendly Python package, especially for people who do like maybe primarily observations and they want to know, how should I pick what to follow up out of the thousands of interesting LSST observations. So this is our end goal, and I've listed my collaborators there. So we use the Kickstarter funds to get a head start on this project, and we have since secured PDART funding from NASA to keep working on this tool. And I'll just note that this part is now available. We have a GitHub repository, and you can now query the JPL system and do a full sampling of an orbit's uncertainty to set up many, many clones to integrate. It was a surprisingly annoying task. There's a lot of subtle coordinate system issues, and the databases don't contain all of the information you need to do this in the same place. So it's kind of a pain. So now there is a nice tool that makes it kind of a one-line thing to set up clones of an object's uncertainty. So that is ready to go and on GitHub if that's something you are interested in. But I'm going to focus the rest of this short talk on how we are dealing with dynamical classifications of TNOs and developing the pieces of the tool that are going to go into that user-friendly Python package. So how are we going to actually classify those 10 or 40,000 TNOs into those different categories so that we can do some science with the detections? So on the left here is an example of a real TNO detected in the AUSIS TNO survey. And we have the observed orbit, the best fit orbit here in eccentricity versus semi-major axis is the triangle. The colored dots are all samples of the orbit fit uncertainties. And we've kind of identified two extreme orbits in the other shapes on the end here. So you can see that this is an object that's pretty far out, 153-ish AU semi-major axis, has a pretty big uncertainty, even though it was observed over several years very carefully. So this might be typical of an early LSST uncertainty for these distant TNOs. There's a big uncertainty in the line of sight velocity of these things because they move so slowly and we don't get as much change in perspective as we'd like. So you get these big uncertainties. And typically how we deal with TNOs is we just integrate these three orbits. So we kind of have a min, best fit, and max clone. And it's limited to 3 because we have to kind of visually inspect the outputs. And here we can see this object has 3 different classifications on those 3 different clones. So it's a pretty uncertain dynamical state. And the problem here is that there's a lot of space in between those clones. It'd be really nice to do, like 1,000 clones of this to get an actual statistical probability that it's really resonant or detached. But we can't do that if we have to visually inspect the outputs. So the solution, of course, as to a lot of things, is let's try to throw machine learning at the problem, because that seems to help in a lot of cases. So the way that works is we start with a correctly labeled training set of data. So let's say we have run numerical integrations of a bunch of different orbits in the TNOs, and they each are given a name, and we have done a bunch of time series analysis to look at features of that data. Like, what was the average semi-major axis? What was the change in semi-major axis? Maybe standard deviations, time derivatives, that sort of thing, of all of the orbital elements of this object. So we build up basically this table of an object, the correct label of what its dynamical behavior should be called, and then a bunch of things we've calculated from the time series of those numerical integrations. And we feed this correctly labeled training set to a nicely prepackaged machine learning algorithm. There's a bunch that you can get in Python. I won't go into the black box of, there's a lot of choices you have to make, but and there's different approaches and different algorithms, but they're all pretty user-friendly because they're these nice Python packages. And basically what that algorithm does is it decides how to use these features you have fed it that are associated with these labels, and assigns statistical weights to each of those features, and designs an algorithm that can come up with, given a set of features, what is the correct label that you should give that object with those features. So you get a classifier out of that, which is basically just a weighting of all of these features of how to make a decision based on the features of what to call the object. So then to see how well it's doing, you feed the trained classifier a testing set. So it's a set of objects with the same features calculated as the training set. And importantly, that you know what the correct labels should be, but you don't give the algorithm the labels. And then it spits out the labels for those things. And it will also give you a confidence estimate of how confident the algorithm is that that's the correct label. So then you check those against what the correct label should be. So I made up all of these examples in this slide, but what you hope is that for things where it gave it a label and a high confidence of that label, it's correct. And then you hope that when it's wrong, it had a low confidence in the label that it gave the object. The idea is that if we have 10,000 new TNOs and the algorithm is pretty accurate, and maybe it only gets a couple percentage of them wrong, if almost all of those wrong ones are low confidence, then maybe you can go back through and do human vetting of just the things where the machine learning algorithm had low confidence in its answer. So that you end up with, maybe 950 of 1,000 objects. You just let the machine learning algorithm classify it. Then the human only has to look at like 50 objects and fix the classification. And then you have a pretty high confidence with low human interaction. And this is just kind of a plot showing from a paper that a grad student, Rachel Smolin, and I put out in 2020, doing a very simple machine learning algorithm for the TNOs. And this is showing some of those data features. And the idea is you can plot, for example, here is the maximum time derivative of one of the changes in the orbital angle versus the log of the semi-major axis standard deviation. And all the different colors are different kinds of TNOs with the correct labels that we predetermined. And the idea is that these data features kind of separate out in these correlation plots. And that's how the machine learning algorithm figures out how to weight the features and separate the objects into different categories. And what Rachel did was just a really simple, just do the most basic time series analysis of the integrations. So averages, minimums, maximums, standard deviations. And that yielded something that was 97% accurate on the set of data that we were using to train and test. And then we had a whole brand new set of TNOs from a new survey. And it was 93% accurate on that brand new set of TNOs. So it's not bad for a first pass at the problem. But we have to do some improvements. We need a more diverse training set, and we need to include the other solar system populations, because this was just the TNOs, and we want to do this for all of the small bodies in the solar system. And we want to give some more thought to what features we're feeding the machine learning algorithm. So some new data features we've been working on for resonant objects. This is a top-down view in a rotating frame with Neptune. And resonant objects, the green and orange here, make this kind of spirograph pattern where they come to perihelion, their closest approach to the sun, at specific locations relative to Neptune. Whereas a non-resonant object in blue here has a uniform perihelion direction over time relative to Neptune because it doesn't care where Neptune. So we can come up with a statistical property, which is, what is the non-uniformity in this perihelion direction? And that also gives us more data. We can tease out different kinds of resonances because not every resonance has the same perihelion pattern. So we can start to get even more information. And the other thing, when you combine this non-uniformity with like changes in the semi-major axis, because as you can see in this example, the resonant clone here has the biggest kind of delta A compared to the detached clone, which has a smaller delta A, or the resonant sticking clone, which alternates between small delta A and big delta A. So these are two critical pieces of information for separating out resonant and non-resonant. So this is another correlation plot where we have delta A on the y-axis and some parameterization of the non-uniformity of that perihelion direction on the y. And each of these different colors is either black is completely non-resonant, we have pink is detached, and then we've got a couple different kinds of resonant objects here in red, orange, and this turquoise. So you can start to tease out even more detail about the resonant populations by putting in these more detailed parameters. So that's something we are actively working on incorporating into the machine learning. Another thing we're doing is creating new data sets, because for each different solar system population we want to make a classifier for, we have to have that correctly labeled training set, which just takes a lot of person hours to build up. So I'm a student who was funded over the summer by the Kickstarter grant, Severance Graham, and she looked through, for example, 402 centaurs that have been observed and carefully classified whether they were resonant or non-resonant, because you can get not just exterior resonances in the TNO population. You can get, for example, this is an interior resonance with Neptune, and she found resonances with all the giant planets in the centaur population, as much as a quarter of the observed objects display some kind of resonant behavior. And that's the kind of thing we would like to know as we discover more of these objects. She's also worked on an asteroid training set, going through the literature and seeing what asteroids have previously been associated with resonances. Interestingly, as the asteroids' orbits get kind of updated over time, you really do have to reintegrate and check these because not all of those identifications are still valid. So these training sets will be used to make other classifiers for other solar system regions. So just to kind of wrap up here, in general, we aren't ready to analyze even 10,000 TNOs, let alone the millions of asteroids, for example, that we are going to get from the LSST observations. But we're making good progress, and I think machine learning in particular is a really important tool for this. Although I will just plug that you have to always be careful when using machine learning because it is going to be biased toward whatever is in your training set. We should expect to see kind of whole new categories of behavior in some of these small body populations, just because of the huge leap forward in the numbers when we get the LSST detections. So we're going to have to be a little bit careful that we don't miss out on interesting new things because we've trained our classifier to just put them in some boring category. We also, with these machine learning, we'll be able to, instead of just looking at like a couple clones to sample those orbit fit uncertainties, we can look at 1,000 and it won't be a problem because the machine will be doing it for us. And in terms of sampling those orbit uncertainties, just remind you, you can use those tools already on GitHub. And the project for developing these tools is kind of on a hiatus as I am transferring grants to a new institution, and that is a bit of a mess. But we should be able to really get rolling again in late 2023 and starting to get these tools online. So with that, I will stop. Thank you.
And thank you, Kat. That was a tremendous talk and a really exciting project. We have time for a couple of questions before we move on to the next talk in this colloquium. And I see Andre Presa has a question in the chat. Andre, could you, in the interest of the recording, read your question out loud?
Sure thing. So you just mentioned this a minute ago. So as you get orbital parameters improved, my question is, how sensitive are you over long integration times to what your outcome is? If you're, for example, trying to figure out whether there was this icy planet that was tossed out or anything, any inferences on that?
Yeah, so it depends on the kind of object. So for like a classical belt TNO, the chaos doesn't really make too much of a mess because it's really kind of bounded chaos region. Like you won't be able to say exactly where something's going to be in the future, but the kind of orbit it's on won't change. But as you're out in the detached population or near these resonances, there will be some objects where that orbit fit is just on the boundary between two different categories, and it's kind of on a chaotic boundary. So really all you're going to be able to do is put a percentage, say like 50-50 that it's in the resonant or not, or what time scale it might stay in the resonance. So we are also going to be calculating chaos indicator parameters, so things like Lyapunov timescales and other chaos indicators from the clones. There's kind of a higher level dynamical characterization. So we might not be able to get a satisfying answer as to exactly what kind of object this is, but we're hoping to identify the ones that are on the kind of chaotic boundaries and label those appropriately as perhaps uncertain, which can be its own kind of interesting category. Hopefully that answers your question.
It does. Thank you.
Thanks, Andre. And I see a follow-up question from Gary Bernstein. Gary, go ahead.
Oh, well, you could get.
Oh, go ahead if you want to just summarize.
Yeah, I don't know how many people on the call know about this, but if you're looking for resonances, there's many possible resonances to look for. And officially, they're only apparent when you plot some combination of a bunch of orbital elements over time. And I would imagine that kind of thing can hide from an ML unless you give it lots and lots of examples of lots and lots of different resonances. So I'm just wondering what prospects are there.
Yeah, so this actually hits on why our current algorithms are so bad, because they're based on actually calculating all of those possible resonant angles. And it can be thousands and thousands of possible resonant angles in like the classical belt, and it's terrible. And that's why the current algorithms are so bad. So for the machine learning, we are not going to be feeding it the actual resonant angles. We are going to feed it the semi-major axis, and eccentricity and inclination evolution are the most important, and that perihelion direction. So the hope is that with high confidence, you can say, this is really looking like it's behaving like a resonant object. And then we'll trigger another algorithm that will try to identify the specific librating resonant angle. Most of the wrong classifications in my current approach that we've been using for like OSIS are just due to the fact that you're finding kind of stupid, really high order angles that aren't meaningful, but they do technically librate for like classical belt objects. So if you can just really quickly kick out all of the non-resonant things based on semi-major axis E and I, then the resonant angle search goes much better. If you're already confident it's resonant, finding that angle isn't as bad. It's if you don't know if it's resonant or not and doing the search by the angle that's bad. So hopefully that is clear.
Yeah,
for the probably
yeah.
2 people on the call who understand what that is about.
Thanks, Gary. And we have time for one more quick question before we move on. In the chat, we have Safwan Ayibe, and I hope I pronounced your name correctly. Please go ahead.
Ajbay, thank you. My question mainly about the classifier. If you have an unbalanced classes in your data, and how you deal with this problem in machine learning classifier, because machine learning have some problem when the unbalanced data become more than 10%, for instance.
Yeah. So this is a real concern on using only observed objects to train the classifier, because what we observe is a biased subset, and you might not get representative samples of everything. So we are also going to work on a synthetic data set, basically making up fake particles. designed to be in different classes to kind of balance that out, to make sure that we are not over or under representing certain kinds of behavior in the training set. And also to try to anticipate some of the new behavior we might see that just happens to be in orbital phase space that hasn't been apparent to current surveys, but because of the nature of LSST, we should be able to probe that phase space better. But yeah, that is kind of my caution on the last summary slide, is like, you have to be very careful what you feed the classifiers, because it affects the outcome. So it's a really good question.
Thank you.
Absolutely. And thank you again, Kat, for a really fascinating talk.
Thank you.
It's time now to move on to Vittorio Braga and his work on pulsating stars. Vittorio, can you share your screen?
Okay, can you see it and can you hear me?
We can see it. You're not yet in full screen.
Ah, it's not in the screen. Oh yeah, sure. No.
There we go. Oh, no.
No?
Not yet.
Ah, okay, wait. Here.
There we go. Okay. Go ahead.
Okay, good morning or afternoon. I'm Vittorio Braga, and I will talk about this metric that we have developed with Marcello Di Crescenzo, which is the PI, and Sergio Reccia here at INAF. So, as the name says, we are interested in pulsating stars. Now, which types of pulsating stars? Basically, three types. Classical Cepheids, which are strictly younger than 300 megayears. Other stars that are strictly older than 10 gigayears, and Miras, which span all the ages, from million years to gigayears. Now, on top of these, on this property of their ages, which allows to span all of the ages of the environments that we are interested in, they are easy to detect because they have quite large amplitudes, especially Miras, which have amplitudes in the optical that can reach up to 6 magnitudes. They are numerous, simply. They are large in numbers. In the galactic bulge, there are almost 100,000 analyses detected. In the Magellanic Clouds, there are thousands of classical Cepheids, and so on. And most importantly, because they are precise standard kernels. In fact, they follow tight, more or less tight, period luminosity relations, and this means that known the period, one can derive the absolute magnitude, and from the absolute magnitude, the extinction, the distance modulus. Now, this technique is incredibly powerful. In fact, one can think about calibrating geometrically this relation. With the calibrated relation, one in turn calibrates the supernovae type 1a in galaxies which host both supernovae type 1a and classical Cepheids. And with the calibrated scale of supernovae, one can derive the most precise estimates for the Hubble constant. The precision has gone down to 1 kilometer a second megaparsec, and also this technique is what is behind the work for the Nobel Prize for the discovery of the accelerated expansion of the universe. So we are talking top class results here. And this concerning Cepheids, because they have very tight relations and they're very bright. Analyses, on the other hand, also have a tight relation, but they are fainter. We can only detect them for now until the era of extremely large telescopes in the local group. But they have the advantage to be very old, to be strictly old. So this means they are ubiquitous, and they can also be used, for example, for galactic for galactic archaeology. They keep information of the early stages. These works have already been done by tracing the structure of, for example, of the halo, which is the most important component due to its relaxation times, which are very long, or for the first time the metallicity distribution below here, the metallicity distribution of the strictly old component, of only the strictly old component of the halo. Also, the auroral stars can be used as metallicity indicators, since their period and also their period luminosity relations, the distance diagnostics, do depend on the iron abundance. So auroral stars are both distance indicators and population tracers. Miras, on the other hand, are extremely bright. In the mid-infrared are even brighter than Cepheids. Now, their period luminosity relations are not so tight and are quite difficult to, quite confused, because there is a difference between O-rich type and the C-rich type Miras. But still, what is important is that they are also age indicators, because their period is correlated with their age. The longer the period of the Mira, the younger is the object. And this is extremely helpful because due to their brightness, one can simply by detecting long period Miras in external galaxies, for example, outside the local group 51 Centaurus A, simply by detecting long period Miras, one can in the halo of these galaxies, one knows already that there has been a merger, and that the merger has happened more or less at the time which matches more or less the ages of Mira stars at the peak of the distribution, that in this case is 450 days. So these are only 3 examples, one for each type of stars, of how powerful are these stars that we are interested in. So why did we develop this metric? We all know that there has been a huge effort in trying to optimize the survey strategy for LSST. That is, there has been an effort in trying to maximize the predicted results for each goal of each science collaboration during the 10 years. And this is, of course, is extremely complicated and has led to a huge wealth of survey strategies that are all available thanks to all available online. And we started to think, how is our science affected by the different strategies? What happens with by changing simply host galaxy, or by changing the type of variable that we're interested in? Could we propose some changes? Of course, it is extremely difficult because the changes should not affect negatively all the other science collaboration. But as declared, the survey strategy is still not fixed and is not immutable. And so we have developed this metric, which is available on GitHub, and takes some input, gives some output, and it has 3 main functions. And now I will show you quickly how this works and what can be obtain by running this metric? Well, first of all, we choose a light curve template. By pulsation models, we generate by setting the mass, the temperature, the chemical composition. We get some specific period and amplitude and the shape of the light curve in each of the bands of LSST. And so we generate synthetic light curve, which are our templates for Lyrae, long period Miras, and classical Cepheids. The second input is the position of the sky, the 3D position of the sky. Right ascension and declination are important not only for the extinction, but because this way we can adopt a survey strategy, and by feeding the right ascension and declination into the survey strategy, we know exactly what is the sampling at that point, and at which time each observation in each band will be performed. And the distance, because we have to shift the templates from their absolute magnitude to the distance that we want to simulate. And of course, by using the OpSim package, we load some survey strategy to see which results, which are the results that we obtain from a given survey strategy. So LST constructor takes all this input and does basically one thing. It delivers the time series, simply magnitudes versus magnitudes, and of course the uncertainty of these magnitudes versus the Julian date, the heliocentric Julian date. This is the R-band time series during the first 2 years for a B-type star in the Large Magellan Cloud, simulated with the baseline 2.0. So we have the time series as if we had observed them. The second step in variability surveys is to estimate the period. We use GATSPy, which is no longer supported, but we are ready to implement the new version. And simply what we do is to use the time series to derive an estimated period from the simulated time series. Note that this period is not exactly the period the true period, the period from the template. But we have already checked that within the first year and a half, it is very easy to recover the periods with a precision better than 1%, or even one order of magnitude smaller. Only for Miras, which have very large periods, 300, 400, 1,000 days, we have to wait, of course, more years. And first step, once we have the time series and we have the period, we can fold the time series, obtain the phased light curve and fit them. Of course, by using 10 years data, we have, and by looking at the Large Magellan Cloud, which is quite bright, we have some extremely well-phased and well-behaved light curves. Things are more interesting when looking into 1 year's data, because we are one of our aim is to know what can we do with what science can we do with the data from the first year. Well, we see here that, for example, in the UNG band, we have not enough points for any type of Fourier series fit. Here we use very low orders, the second or the third, not more. So not even with second order fit is possible to fit with a second order series is possible to fit the UNG bands. And for example, things like this can happen, diverging fits when there is a large gap in phase between two phase points. And of course, also for the others, we have a very rough estimate of which is the fit, but we don't know what happens in the gaps. So we run a variety of tests. For example, we want to see whether an AB-type star with period of 0.56 days, typical AB-type star, can be detected in all of the dwarf galaxies of the local group. And what we found is that we know which is the detection limit for the single exposure, because we need the single exposure, of course, being these variable stars. We know which is the 5 sigma limit, detection limit for each exposure. And we found that, for example, for this type of stars, Leo 1 is more or less the threshold. That is, for galaxies closer than Leo 1, at 260 kiloparsec, we can recover easily the light curve, all the points of the light curve in all the bands. And for galaxies that are farther than Leo 1, we would probably not be able to recover these types of variable stars. So we already know how far we can get for these types of pulsators. Long period variables, or MIRAs, are also extremely interesting because, as I told you, they have amplitudes that they can reach up to 6 magnitudes. So it can happen that part of their pulsation is above the detection limit and part is below. And the same, and we are interested in knowing in which range we can move to stay always above the detection limit. And the same happens with saturation. And this is even more interesting because, for example, in fornax, in the dwarf spheroidal fornax, we would recover the 100% of the points, of the phase points, will be non-saturated in the U band, but we will have all saturated points in the Y band and intermediate, and we will have intermediate values for all the other bands. So this means that this can change within the same environment. In this case, these dwarf galaxy, and this changes with the filter. So we are. So this means, for example, that we will take advantage in survey strategies favoring a little more the UNG filter. One last example here. How does the strategy affect sampling? We are using a parameter called the uniformity from Kolmogorov-Smirnov analysis, and which simply tells us how evenly is the light curve sampled. And again, here we see that, for example, the blue one, which is the survey strategy with more points collected in the U and the G, provides a smaller uniformity. Smaller means better for the U, especially for the UNG band, while not making the other bands worse. While, for example, the red one, which is baseline 2.1, is generally worse for all of these. So these are some of the tests that we have run. Now we are still working on this to improve this metric. For example, we want to include the simulation of blending because we might be interested, of course, in the bulge or in the inner regions of the most dense dwarf spheroidals. So we want to see how blending can affect our results. We will, as I said, implement GATSPY. This metric initially was should have been included in the math, but it is too specific. We don't know if in the future it will be possible to include it. And there will be a publication soon. Probably we will submit this week we will submit a letter this week for this metric. And that's it.
Thank you very much, Vittorio. That's another excellent talk. And I'm delighted to hear that you're planning to publish shortly. That's great news. So if you have any questions, we have time for a couple of quick questions. So please post them in the chat. And to get the ball rolling, I have one question of my own. Having experimented with your metric as part of the work that I've been doing, I know it has a common feature of a lot of software that analyzes periodicities in that it is quite computationally intensive. And that means it takes quite a long time to apply it to a single opsim, but to apply it systematically to a lot of opsims is, so far, it's been very difficult to do. Do you have any prospects for addressing that?
Well, I am quite sure that the version that you checked is let's say that we have something newer that is a little faster. We did not focus for the moment in improving, in increasing the speed, but just in making the output more clear, because as you might have noticed, there were for example, some outputs were overwritten. Now there is no more this problem. But of course, if, let's say, if there is the possibility to put the math, we will think about making it usable for a large for very intensive runs. So we will have either to parallelize or find some solution. This is not our priority for the moment. We want to complete with the blending. We want to first solve the blending issue, and then this could be our second, let's say, our second priority point.
Fair enough. Fair enough. Thank you. And I see we have another couple of questions from the chat. Once again, a reminder, if you could kindly read your question for the benefit of the recording. So first of all, we have Michelle Travucci. Michelle, you are ever so quiet.
Is it better?
Oh, that's better.
Yes.
Okay. Thank you, Vittorio, for this interesting talk. My question concerns the long period of variables, and specifically, we talked about Miras, and I was wondering if you also considered some of the largest amplitude semi-regular variables sometimes behave closely to Miras, and in some other cases display multi-periodicity. So my question would be, is it possible to apply this metric to multi-periodic variables, maybe displaying just a couple of periods instead of just one? Did you made any tests concerning this?
I can tell you, for the moment, we are focusing on strictly periodic variables. Of course, myriad themselves are not even strictly periodic. We are relying on the models by Trabucchi. I don't remember the year. I think it's 2016. I don't remember correctly.
It's later. That's my paper, actually.
Okay.
That you're using that.
Okay. So let's say that we have to give priority to a few types of well-behaved objects. I can mention this, and we can see if this works, because this is quite easy to implement. We should simply need a new input here. We should simply need a new input. We shouldn't have to change the metrics, or at least we shouldn't have to change the metrics significantly. So this can be something we can think about. We can start with a template, see what happens, and see if the metric has to be if we have to change the metric in order, for example, to account for the non exactly regular variability of these objects. But in principle, we just need a different table of inputs, which is quite easy. We still didn't do this, but
okay, thank you very much.
And I see we have time for one more question from Andre Prisa. Andre, go ahead and read your question.
Thank you. I was just wondering, you mostly talked about the wide as deep part of the survey. So my first question is whether you can comment on how this would work in the deep drilling fields. And my second question is whether you can comment on how the fact that we have 6 colors, 4 of which will be reasonably well represented, how does that affect your ability to classify thoroughly?
Again, for concerning the deep survey, we simply have to just feed a different opsim run into the metrics. So this is in principle quite easy. Concerning the second part of your question, we didn't really focus on the classification. Let's say these metrics, for the moment, and probably also in the future, will not focus on estimating a period, then an amplitude, the shape of the light curve. Of course, these are all things that the metrics does. But in the end, for example, a classification, the classification would be, for the classification, we should write some independent piece of code, which is completely independent from the metrics. Of course, if something like this available, we could provide some input. To a classification matrix, but this would be two separate pieces of code, and as Rachel said, by how it is built, this is quite a slow metric, and of course, even if we might think to improve, to make it faster, this will not be at all suitable for classification, not even, and to provide very large samples of stars for example, for training neural network, or whichever other method you think to use. But still, the output can be used by another piece of code for classification.
Absolutely. Well, thank you very much, Vittorio. And that's all the time we have for questions right now. So let me thank Kat and Vittorio very much for 2 fascinating talks. Those are really 2 excellent projects. And before we wrap up, I just wanted to say a reminder that we have 2 more Kickstarter colloquia this week, with talks tomorrow and Thursday. Tomorrow we'll be hearing a talk about eclipsing binaries from Andre Prisa, and on stellar systems from Adriano Pierres and his whole team. So I hope you'll be able to join us for those events as well. And thank you all very much for coming. I'll see you next time.